Okay, so now let's proceed to some slightly more complex switch capacitor circuits, right?
Okay.
Let's start with so let's look at this case. Okay, you have a voltage source VDD, a switch S1, okay, controlling a capacitor C,
Okay.
switch S2, okay, and let's say there is a current source
Okay.
I naught here, okay,
Yes.
and maybe to make it more practical, let me put a resistor,
Okay.
okay, RC, right, and then we'll look at more interesting corner cases going forward, okay. So now the idea is we are going to control these two switches using with some time this thing. So
Yes.
you have a control C1, C2 signals, okay, where C1 is let's say it is,
Maybe we can call them S1 and S2 so that they don't get confused with the capacitors.
oh yeah, correct, okay. So yeah, we'll just call the control signals S1 and S2 as well.
Yeah.
And when S1 is high, it means the switch is closed.
Yes.
Okay, and when S2 is high, it means the switch S2 is closed.
Yes.
Right, and we will ensure that S1 and S2 are not close together.
Close together.
Right, we'll not, for now we will not get
In fact, we can also look at that case now that you have added a resistance R.
So we can look at that case
Yes.
later, but for now we will just deal with this. Okay, so I have my time. So this is T1. Okay, this is S1, and then S2 is basically 0, and then at T1 it goes high all the way to T2 and then back, and maybe S1 then goes high again. Okay, so this is S1, this is S2, and this is time T2.
Yeah.
Right, so or I could say, for example, this is time T1, okay, and this is time T2, okay.
Yes.
And then it repeats.
Yes.
Okay, so let's look at that case. T1, and then it's going to repeat with periodically like this.
Okay.
So first, before we go ahead, so what I want to do now is I want to just observe this capacitor voltage. I want to observe the capacitor voltage and understand what is going to happen to this voltage,
Okay.
right? And maybe we'll look at various quantities that you can calculate out of that. So the first idea is to plot it as a function of time.
Okay.
Okay, yeah. So so intuitively, so how would we start now?
Okay. So.
By the way, just to clarify, T1 is large, T2 is also large.
Large.
Okay, they are not. We are assuming that they are sufficiently large. How large we will
Sure.
quantify. Yeah.
Sure. So let us say that okay. So if T1 is very large, I'm going to start by first I need to know the initial voltage across the capacitor.
Capacitor, right? So initially it was discharged.
It is
right?
discharged.
There is no this
Okay.
thing. Yeah.
So first S1 is closing.
Yes.
So S2 is open. So I don't need to worry about the current source.
Correct.
So then what happens is that the capacitor will charge exponentially to VDD.
It will charge to exponentially to VDD. Yes.
Right? Through switch S1 and
Exactly.
R1.
So first thing we can do is when S1 equals 1 and S2 equals 0, the circuit is going to look like this. Right? So we reduce it to a circuit that we already know.
Yes.
Okay? Yeah. So it's going to look like this.
Yes.
And which is why you said that this is going to be an exponential charge.
Correct.
Okay. So this is VC of t. And the VC of t, we also know the exact equation. It
That's
should
right.
be VDD into 1 minus e power minus t by RC. So how large should T1 be? It should be large enough compared to RC.
Correct.
Right? So to be safe, we can assume that it's 100 times the time constant or something
Yes.
like that. So
Yes.
assume T1 is approximately 100 times RC.
Yes.
It's a large enough time for it to go all the way. Practically, this exponential charge up will even hit
Yes.
VDD, is what we can assume in this case. Yes.
Yes.
Yeah. And now, what happens to in the second phase when S2
Yes.
is 1? So, how do we analyze that?
Okay. So now in the second, when S1 is 0 and S1 is 0 and S2 is 1,
Yeah.
then switch S1 is opened.
Yeah.
In fact, there can be no current through R1 then.
Correct. Exactly. Yeah.
So my guess is that this I0 is just going to discharge the capacitor.
Right. So, effectively, when S1 equals 0 and S2 equals 1, the effective capacitor, effective circuit is going to look
Yes.
like this, I0 and C.
Yes.
Right? The resistor is basically hanging like this because S1 is open,
That's right.
and therefore it doesn't even come into the picture. It is not part of the circuit, active circuit that is working.
That's right.
Okay, and this is something we have already seen.
Yes.
Now we know that the capacitor initially is starting off at VDD.
That's right.
Right,
Now it is
and
correct.
there is a current source that is trying to discharge this.
Correct.
And therefore we know that the equation, right,
Yes.
should be VDD minus I0 by C into T.
That's right.
Right, this is the equation that the
That's
thing
right.
should follow. So therefore now I could actually plot this VC of T as a function of time.
Yes.
As a function of time. Okay, and so I'm going to look at till time T1. Okay, then time T1 plus T2. Okay, then again, or should we just for simplicity call everything as T?
Sure.
T is just large
That's right.
enough, right?
That's right.
So T1 is 100 RC, and most importantly, even in this case,
Yes.
we need to ensure that this time
Yes.
T2 is sufficiently larger compared to
Yeah. So if you do that, then the voltage goes negative. So
exactly.
maybe what we will do, we'll do this. We'll assume that T2 is such that it is CVDD by I0.
Yes, great. That's
Can we
a
do
good
that?
idea. So T2 we are going to assume is CVDD by I0.
I0. Yes.
Okay, that's a great point. Okay, so this is T1, T2, T1.
Yes.
So T1 should be very large,
That's right.
But-
100 RC.
100 RC, but T2 should
Yes.
be exactly equal to CVDD by I0.
Yes.
Okay,
Yes.
so great. So then we should basically redraw this, right? So this is going to be T1 plus T2,
That's right.
right?
That's
and
right.
then we'll see what happens.
We'll see what happens.
Okay.
Yes.
Yeah. So what we go ahead and do now is to plot this voltage as a function of time. So till this, right? So this is VDD. This is your VDD by 2.
Yes.
Okay. So we are assuming that
The time constant is 100th of T1.
100.
So
right?
it goes. I think
so
you won't
I'll-
even be able to see VDD by 2
exactly.
on this graph.
Yeah. So it will very quickly charge up.
Yes.
Slightly exaggerated curve
Correct.
right here.
That's right.
Then at T1 you're switching and getting the current source to be active.
That's right.
This will drop linearly with time all the way
And
to
if T2 is CVDD by I0,
yes,
VC of T will go exactly to 0.
exactly to 0. It will not go any further.
That's right.
And then you are again switching back to essentially this
That's right. In
voltage
the third
source
cycle, S1 is on, S2 is off again.
S2 is off again, right?
That's
and
right.
therefore again this one, if you look at this, again this is T1. Okay, this is 2T1 plus T2,
Yes.
right? And you have another thing which is 2T1 plus 2T2,
Yes.
right? So this again will go up exponentially, sorry, charge up, and then it will again drop
Yes.
to this.
And this will keep repeating.
This will simply keep repeating over and over again.
This is an interesting shape. So you have an
yeah.
exponential on one side and then a linear drop on the other side.
Linear
Yeah.
drop on the other side,
Yes.
right? So now we could, calculate some interesting, things. So for example, how much of energy, right, has the voltage source delivered, right?
Yes.
And how much of energy is ultimately going, to the so let's look at that.
Yes.
For example, right, let's look at the energy that is delivered by the voltage source, right? So if you look at this this case, in the initial part, S1 is closed and S2 is open.
Yes.
It's a first order RC this thing. So we know that the supply should simply deliver C VDD squared.
C VDD squared.
Right?
Correct.
Exactly. So let's look at that part. Right?
So during S1 equal
Yeah.
to 1.
So this is
Yes.
during S1 equal to 1 and S2 equal to 0.
Yes.
Right? Energy delivered by the source, by the voltage source,
By the voltage source.
equal to C VDD squared,
Yes.
right? And so energy that is stored in the capacitor
Yes.
is half C VDD square. Okay.
Yes.
And now what are we looking at? We are looking at, of course, the
S2.
remaining half.
Yes.
Remaining half C VDD squared we already saw.
It goes
is
through
going to-
R1.
Is going to get discharged. Is going to
Discharged.
dissipate through the resistor.
The resistor R.
R, right?
Yes.
So now if you look at this, so what happens now to the energy that is, so should we plot, can we plot the power? So what can we plot with respect to power? Should we be plotting power as a function of time, or should we be plotting energy as a function of time of the capacitor?
Well, energy we have integrated. These energies are to infinity.
Exactly.
So it's going to be. We cannot plot it as a
We
function
cannot
of
plot it
time.
as a function of
We
time.
can plot the power as a function of
As
time.
a function of time,
Right.
Okay, right. So effectively we are saying that the capacitor stored half CVDD squared.
Yes.
Then you connected the current source that simply discharged this thing. So
Yes.
if you look at the energy delivered by the voltage source in a time t1 to t0 to t1 plus t2,
Yes.
it is still CVDD squared.
It's still C VDD
Right?
squared. Correct.
And in the end of T2, there is
Yes.
no energy available in the capacitor either.
That's
Right?
correct.
The current source has discharged it and taken
Correct. So in fact, the energy has gone into the current source.
it. Exactly.
That all of half C VDD squared would have most likely gone into the current source.
Exactly.
Because
Right?
unlike an exponential charging,
Yes.
the energy, because it's a ramp,
Yeah.
I suspect that all of half C VDD squared should, maybe we
Exactly.
should do that.
Yes.
In cycle S2,
Yes.
we should calculate, because the capacitor is completely discharged,
Yeah.
we should try to calculate how much power has gone into the current source.
Into the current source. Okay.
Yes.
That's a great thing. Okay. So let's go ahead and do that. Right. In S2 equal to 1 and S1 equal to 0.
Yes.
Right. Okay. So in this case, or rather I should say when. Okay. Yeah.
Right.
So what is happening is,
So one thing we can say is the voltage source is open circuited.
Yeah.
So there is no energy coming out of the power or energy coming out of the
coming out
voltage
of the
source.
voltage source.
Okay.
Right? So you
And
have-
R is also open circuited, so no energy or power
Exactly.
dissipated.
So the effective circuit is
Is
just
this,
right?
right?
And initially, I'll not say T equal to 0 minus.
Correct. So maybe we can just write down saying initial energy across in the stored in the capacitor is
Yeah.
half C VDD squared.
Yes.
Final
Initially,
energy is
half C VDD square. Final
energy is 0.
equal to 0.
Yes.
Okay.
So during this cycle, we just want to find out how much energy has entered the current source.
Has entered the current source. So how do we do that? We again, I'm guessing we write the instantaneous power.
That's right.
Which is basically Vc of t
Times I
into
naught.
I naught.
Yes.
Right? and we are going to now integrate this.
Correct. And VC of t was basically VDD into VDD minus I naught by R times T.
I naught by
I naught
C.
by C times T. Right? This was the equation.
Right, into I naught.
Correct.
Right, and
That's
then
right.
we are going to look at the integration. Okay, good. So
That's
I
right.
think this is interesting. So we can write this as VDD I naught
Yes.
minus I naught by I naught squared by C into T.
That's right.
Right? Okay.
And we are going to integrate this from 0 because we are now, the new reference time is 0
Yeah.
for this equation.
T2.
Till T2. And T2 was also
chosen carefully.
was chosen carefully.
Was
right?
chosen very carefully.
CVDD by I naught.
Yes.
So we'll have to do that integral
Exactly.
and see what it is.
Okay, so what we can do is, so we will again, so let's
Yeah.
write
So
that
energy
out.
EI.
EI is basically going from, so should be careful, you're saying not to go to infinity.
Yes.
Okay.
So it should go from 0 to T2.
0 to T2. I think,
Yes.
yeah, this is very important. Okay. So what we have is
Pi of T.
Yeah. Pi of T
dt.
dt. 0 to T2, and this is VDD I naught minus I naught squared by C into T dt. Okay, yeah, great. So this is VDD I naught into T2,
Correct.
right, minus I naught squared by C into T2 squared by 2.
Correct.
Okay. Now what did we say T2 was? We said it has to be C VDD by I naught.
Correct.
Okay. Therefore, EI is going to be VDD into I naught to C VDD by I naught, right?
Yes.
Minus I naught squared by C into C square VDD squared
By 2 I naught squared.
by 2
I naught squared.
I naught squared. Yes.
Interesting. Okay.
This is again very interesting. This thing cancels
Yes.
out. Capacitor, this cancels out. I naught. Okay. So you get C
VDD
squared minus half C VDD squared. Which again we know
Half
the
C
magic
VDD
number.
squared. Yes.
Half C
VDD squared.
VDD squared.
So interestingly, so it looks like the capacitor initially had an energy of half CVDD squared. It has gone completely into the current source.
Into the current source.
Right, the current source is basically absorbed power.
Exactly.
And we know this, right? We know it is
exactly.
possible for ideal voltage sources, ideal current sources to absorb
power.
Absorb
Yes,
power
exactly.
as well.
In fact, I just want to just go back and redo this calculation with the other trick that we had followed.
Yes.
Okay. So
Yes.
Pi of T is Vc of T into I naught. Okay. And we said that EI is integral Pi of T dt. Right. So this I will write as I naught into Vc of T into dt.
Yes.
Okay. Now let's see what we get out of this.
Yes.
Integral Vc of T dt.
Yes.
What is this with respect to the current in the,
Yes.
right?
Yes. So you can now write the expression for Vc of T
Yeah.
as VDD minus, is that what you want to do?
No.
Ah.
I am looking at, if I see the current through the capacitor,
Yes.
IC of T is C dVc by dt. Right?
Correct.
So integral.
So, but unfortunately that is, okay, that is I naught
yeah, that
Right.
is, and this is equal to minus I naught.
is equal to minus I naught,
Yeah.
right?
So
So basically you want to write minus I naught dt as C
correct.
dVc.
So exactly. So we can write I naught here
Yes.
as minus C dVc by
Correct.
dt. Okay,
Correct.
we substitute that in the integral.
Times Vc of T dt.
EI therefore
Yeah,
is
that's right.
minus C dVc by dt into Vc of t dt,
Yes, absolutely.
right? I can do this, right? Minus C Vc dVc.
Correct.
This is going from
It needs to go from VDD to 0.
VDD to 0.
That's right.
Exactly. Right?
Because at
And
time
therefore-
0 it was at VDD.
Correct.
At
Exactly.
time T2 it was
at t
0.
equal to infinity, it is going down to, yeah, I mean
That's
at t2. Correct. Yeah.
Correct.
So you get minus, so you get plus C half C VDD square.
Perfect.
Again,
Perfect.
you've been able to get this in two different ways, right?
That's right.
So even though the current source I naught was a constant, we were able to write this as C dVc by dt, right?
That's right.
And which is what got us this final answer, right? So this is interesting. So clearly the energy, so there is a voltage source supplying energy, that energy is being lost into the current source. Again, you supply energy, it's being lost into the current source.
And so on.
And so on. This goes on forever. Okay.